This is our low-level interfacing IoT project. Our project combines an accelerometer, an RGB LED, and Bluetooth low energy on a Raspberry Pi Pico W. The context of this project is it is basically a way for friends and family to communicate with each other from across the globe without needing screen time, as in this digital age, screen time is increasing, and it's good to get away from it. So it's essentially a mood light that connects to your phone, so it changes color or the mood based on the movement of the device. For example, blue, sad, yellow, happy, etc. And when your phone connects to it, it gets brighter the closer you get to it. So you basically know when that person is in the room. So now I'll go through the code before demonstrating the technology in action afterwards. So the imports and setup, as you can see at the top of my code, I imported MicroPython libraries needed for. The machine library controls hardware pins, time adds delays, NeoPixel drives the RGB LED, and Bluetooth handles all the BLE communication. I also imported my accelerometer class from another file to read motion data. And below are some Bluetooth constants and an UUID defined, which are unique identifiers. So other devices, for example, my phone I'll be using in this explanation, or a laptop, etc., can recognize my Pico over BLE. So now the BLE device class, this handles all the Bluetooth logic. When the class starts, it turns the Bluetooth on, registers a small BLE service that can send and receive data, starts the advertising so that my phone can find it in the NRF Connect app, and also starts scanning so it can listen for other devices nearby. Whenever a Bluetooth event happens, like connecting, disconnecting, or finding a nearby device, the IRQ function starts. Inside IRQ, whenever a scan is detected, I grab the RSSI value, which is the Bluetooth signal strength, and that is measured in decibels. And it is essentially the distance between the Bluetooth device and the Raspberry Pico. This value gets stored in self.lastScan or SSI, and updates every time a BLE packet is received. So this class gives a live RSSI reading from my Bluetooth connection and also handles notifying the phone about brightness value. Next is the map_val function. This little function is used all over the code and it essentially maps one range of numbers into another. For example, my accelerometer outputs values between plus and minus 16,000 when getting the coordinates of the movement. But I want to turn that into a range from 0 to 255 so it fits my LED color system. So this is what that function does. It's also used to turn my RSSI values, which are usually from between minus 30 to minus 90, into a brightness level between 50 and 255. Next is the gesture_RSSI_lamp function. It's the main program that ties everything together. It sets up the I2 connection to the accelerometer, and then it sets up the NeoPixel LED on pin 7. After that, it creates a BLE device object to start Bluetooth advertising and scanning. Once everything's running, the code enters an infinite loop that constantly reads the tilt of the Pico using the accelerometer. The x-axis reading is turned into a hue value, which is basically a color position on the RGB wheel. It reads the RSSI from Bluetooth, which depends on how close my phone is or the connected device. This gets turned into a brightness value using the mapping function. Then, using some simple math, it converts the hue into red, green, and blue values and scales those by the brightness. Finally, those color values are sent to the LED and it lights up in real time. So when I tilt the board, the color changes, and then when I move my phone closer or farther away, the brightness increases or decreases. It also prints out the current RSSI brightness color values in the serial monitor so I can see what's happening behind the scenes. In summary, the accelerometer provides motion data over I2C, Bluetooth provides signal strength through RSSI, NeoPixel LED visualizes both pieces of data together. Next, we'll show you the example.
I'm just going to quickly run through the three main components on our breadboard. These are the Raspberry Pi Pico board, the accelerometer, and then the RGB down the bottom. So first up, the Raspberry Pi Pico. It's the microcontroller that runs the entire project. It's small but a very powerful chip. I'm using it to process the sensor data coming from the accelerometer and control the output to the RGB. It connects to the breadboard using pins in the base, and it's been programmed using Python. Next, then, the accelerometer. This sensor measures acceleration and movement in three dimensions, X, Y, and Z. In this setup, it detects motion or tilt, and we can use the data that comes from it to control the RGB lights. So in our case, the lights change colors as the board is tilted from side to side. And then finally, the RGB. Each LED can produce a mix of red, green, and blue light to create a wide range of colors. It's connected to the Raspberry Pi Pico, which controls the color and brightness. Controls the color based on the accelerometer's reading, and then controls the brightness based on the strength of the Bluetooth signal coming from the phone that's connected to the device. So that's just a quick run through of the components, and we'll show a example of the board actually working now. So this is a quick video to demonstrate the use of our system. On our breadboard here, we've got our Raspberry Pi Pico, the accelerometer, and then the RGB. They are the main components that we've used in our system. So our user can tilt their lamp from side to side to switch the colors. That changes the effective mood setting for the lamp. And then, as Ben's demonstrating here, as the phone moves closer and further away from the lamp, the brightness on the light, which unfortunately isn't been picked up very well, is changing from dim. You can see on the RSSI value here, the value is changing as Ben moves his phone from left to right, so further and closer from our breadboard. So that's increasing the distance of the Bluetooth, which increases the RSSI value, and then that in turn decreases the brightness. So you can tell how close or how far away the user's phone is from the light based on the Bluetooth strength.